It's May 2026, and after nearly 3 months of continuous operations over the Persian Gulf, one reality has become impossible to ignore. The United States has demonstrated that it can establish air superiority against a sophisticated regional military. Yet behind every successful sortie lies a different question: what comes after today's generation of fighter aircraft? For nearly 90 days, American pilots have flown missions almost without interruption. Advanced fighters, carrier-minded space strike aircraft, strategic bombers, surveillance platforms, aerial refueling tankers, and electronic warfare aircraft have operated together in one of the world's most closely watched theaters. From precision strikes to intelligence collection, the campaign has highlighted the extraordinary capabilities of modern air power, but it has also revealed its limits. Every mission requires logistics. Every sortie depends on fuel, maintenance, intelligence, satellite communications, and a complex chain of supporting aircraft operating far from the battlefield. Even the most advanced fighter is only one piece of a much larger system. That is why defense planners are already looking beyond today's fleet. Because the next generation of warfare may not be defined simply by faster aircraft or better missiles. It may be defined by something much larger, an entirely new way of fighting. Recent defense announcements suggest that the United States is accelerating development of what is expected to become its first sixth-generation fighter aircraft, widely referred to as the F-47. While many details remain classified, publicly released information paints a picture of an aircraft designed not merely to replace existing fighters, but to reshape the relationship between pilots, artificial intelligence, unmanned systems, and the battlefield itself. Unlike previous transitions from the F-15 to the F-22, or from the F-22 to the F-35, this is not simply another step forward in performance. It represents a shift in operational philosophy. Modern fifth-generation aircraft were built to survive inside heavily defended airspace. Their stealth characteristics reduced radar detection, allowing them to strike targets that earlier generations could never safely approach. The next generation appears to pursue a different goal altogether. Instead of sending one aircraft into hostile airspace, future operations may involve an entire network of autonomous systems working together under the supervision of a single pilot. Rather than acting as the lone hunter, the fighter becomes the battlefield commander. That concept changes almost everything. For decades, American air strategy has depended heavily on aerial refueling. Tanker aircraft extended the range of fighters, allowing operations thousands of miles from home bases. Potential adversaries recognized that dependence and invested heavily in long-range missile systems specifically designed to threaten those vulnerable support aircraft. The future fighter possesses dramatically greater unrefueled range. That equation begins to change. Instead of relying on a vulnerable logistics chain close to contested airspace, aircraft could operate from much greater distances while maintaining combat effectiveness. That would complicate the planning assumptions behind many modern non-access strategies that have been developed over the past 2 decades. Range alone, however, is only part of the story. Stealth technology continues to evolve as well. Earlier stealth aircraft focused primarily on reducing radar signatures from certain directions and across selected frequency bands. Future designs are expected to pursue a far more comprehensive approach, attempting to reduce detection across multiple sensor types simultaneously, including radar, infrared, and other electromagnetic signatures. Achieving that requires more than new materials. It influences the entire shape of the aircraft. Tailless configurations, advanced thermal management, embedded sensors, and new manufacturing techniques all become part of the same engineering challenge, reducing visibility while maintaining performance. The result is an aircraft that may look very different from the fighters that have dominated military aviation over the past 30 years. Propulsion is undergoing an equally significant transformation. Publicly available information suggests that the engines being developed for this new generation emphasize adaptability rather than simply producing more thrust. Instead of operating efficiently under only one set of conditions, adaptive minus-cycle engines are designed to optimize performance for different phases of flight. During high-speed combat, maximum thrust becomes the priority. During long-distance patrols, fuel efficiency becomes more important. The ability to shift between those modes offers obvious operational advantages, extending range while reducing logistical demands. But perhaps the most important change has nothing to do with speed. It has to do with electricity. Modern fighter aircraft consume vastly more electrical power than previous generations because their sensors, electronic warfare suites, communication systems, and onboard computers have become increasingly sophisticated. Future concepts may require even greater electrical capacity. particularly if advanced defensive technologies such as directed energy systems eventually mature into operational capability, whether those systems arrive soon or remain years away. Today's engine designs appear intended to support that future rather than simply meet today's requirements. Development, of course, is never without setbacks. Every major aviation program experiences failures during testing. Flight software must be refined. Autonomous systems require thousands of hours of evaluation. Prototype aircraft reveal problems that only become visible outside the laboratory. Those setbacks are not necessarily signs of failure. They are often evidence that real testing is taking place. The history of military aviation is filled with prototypes that encountered serious technical challenges before evolving into some of the most successful aircraft ever built. That process remains true today. Meanwhile, autonomous aircraft have begun moving from concept to operational reality. Rather than replacing pilots, current development focuses on creating collaborative systems capable of flying alongside manned aircraft. These unmanned wingmen could perform reconnaissance, electronic attack, air defense suppression, or even carry weapons themselves while remaining under human supervision. Instead of risking a pilot inside the most dangerous portion of contested airspace, commanders could send autonomous systems forward first, gathering intelligence, identifying threats, and forcing enemy defenses to reveal their positions. Only then would the manned aircraft need to commit. That approach fundamentally changes risk management in modern air warfare. Rather than concentrating capability inside one extremely expensive aircraft, military planners distribute capability across an entire network. The networks, unlike individual platforms, are much harder to defeat. The implications extend well beyond any single aircraft. For years, military analysts have described future conflict as a contest between networks rather than platforms. The aircraft itself is becoming only one node inside a much larger combat architecture that includes satellites, artificial intelligence, electronic warfare systems, cyber capabilities, autonomous aircraft, and space-based communications. That broader architecture may ultimately prove more important than the fighter carrying the pilot. One of the defining features expected for future air operations is the concept of collaborative combat aircraft autonomous wingmen capable of operating alongside a single manned fighter. Public defense planning suggests that future force structures could include multiple unmanned aircraft supporting each crewed platform, allowing commanders to distribute sensors, weapons, and electronic warfare capabilities across an entire formation rather than concentrating them inside one cockpit. Instead of entering contested airspace alone, a pilot may command an entire package of autonomous systems. Some drones could fly ahead as reconnaissance platforms, identifying radar emissions before enemy operators even realize they've been detected. Others could serve as electronic decoys, intentionally drawing missile launches away from more valuable aircraft. Additional platforms might carry long-range air-to-air missiles or precision-guided munitions, engaging targets while the crewed aircraft remains well outside the highest risk areas. In that environment, the fighter pilot increasingly resembles a mission commander rather than simply an aircraft operator. Artificial intelligence becomes the force multiplier. Machine-learning algorithms can process enormous amounts of sensor information far faster than any human crew, rather than overwhelming pilots with hundreds of separate radar racks. Future systems may automatically prioritize threats, recommend responses, coordinate manned teammates, and continuously update the tactical picture in real time. The human still makes the final decision, but the speed at which information is processed changes dramatically. This evolution also explains why military planners increasingly emphasize software, networking, and data integration alongside traditional aircraft performance. A faster airplane alone no longer guarantees superiority. The aircraft that shares information most effectively may ultimately prove more valuable than the one with the highest top speed. These developments also influence strategic competition beyond the Middle East. Across the Indo-Pacific, military modernization has accelerated rapidly over the past decade. Multiple nations continue investing heavily in advanced aircraft, long-range missile systems, integrated air defenses, cyber capabilities, and space-based surveillance. At the same time, several countries are pursuing their own next-generation fighter programs, each seeking to shape the future balance of air power. From a technological perspective, that competition extends far beyond airframes. Engines, composite materials, advanced semiconductors, manufacturing precision, sensor fusion, artificial intelligence, and secure communications all become equally important pieces of the equation. Developing those technologies requires years of research, industrial capacity, highly specialized engineering talent, and enormous financial investment. Blueprints alone cannot create that ecosystem. History repeatedly demonstrates that advanced aerospace programs succeed not simply because of innovative designs, but because of decades spent building the industrial foundation capable of producing them reliably. That remains one of the greatest challenges facing every nation attempting to field a sixth-generation capability. Meanwhile, recent operations in the Persian Gulf continue offering lessons about the present. The campaign has shown that precision air power can rapidly suppress large portions of an integrated air-defense network when supported by intelligence, electronic warfare, and long-range strike capabilities. At the same time, it has also demonstrated that military success does not automatically translate into political resolution. Infrastructure can be damaged. Radar stations can be replaced. Missile batteries can be relocated. Adversaries adapt. Every conflict produces a cycle of action, adjustment, and counter-Midas adjustment. Technology accelerates that cycle, but it rarely eliminates it. That is why many defense analysts argue that future deterrence depends not only on possessing advanced platforms, but on convincing potential adversaries that those capabilities can be integrated into a larger operational system capable of responding faster than they can adapt. The aircraft matters. The network matters even more. Behind every discussion of sixth-generation fighters lies another question that receives far less attention cost. Modern military aviation has become extraordinarily expensive. Developing a single advanced aircraft requires billions of dollars before the first operational squadron ever becomes combat-ready. Training pilots, maintaining sophisticated engines, producing specialized components, and sustaining global logistics networks all contribute to the overall investment. For taxpayers, those numbers naturally raise difficult questions. Does greater technological superiority reduce the likelihood of future wars? Or does every new generation simply encourage competitors to invest even more heavily in developing countermeasures? History offers examples supporting both arguments. Stealth reshaped military aviation. Precision-guided weapons transformed strike operations. Network-centric warfare fundamentally changed battlefield awareness. Yet conflicts have continued to evolve alongside each technological breakthrough. Every innovation eventually inspires adaptation. That reality may represent the single most important lesson emerging from today's defense modernization efforts. The goal is not to build an invincible aircraft. History suggests such a platform has never existed. Instead, the objective is to maintain enough technological advantage that potential adversaries conclude confrontation carries unacceptable uncertainty. Deterrence has always been as much psychological as technological. The aircraft itself becomes part of the message. The announcement of major procurement programs, increased research funding, expanded autonomous systems, and closer integration between air, space, and cyber capabilities all communicate something beyond simple military capability. They signal long-term strategic intent. Whether discussing Europe, the Indo-Pacific, or the Middle East, that message remains remarkably consistent. Future conflicts will not be decided by individual platforms operating independently. They will be decided by connected systems capable of sharing information, coordinating decisions, and adapting faster than their opponents. In many ways, that transition has already begun. The fighter pilot of tomorrow